try to capture the lectures on video, and see how we go from here. All right. So today, what are we talking about today? Art to part. Good. Good. I came to the right class. Go ahead. Right. All right, so art to part. Is that it? Oh, look at that. Full screen.
Selfie. But first, let me take a selfie.
All right, so art to part. What do we mean when we say art to part?
Going from dimensions or an idea to a physical static.
So you want to go from
Concept design to model.
as well. I didn't hear the echo when I was testing it before, but I guess we're stuck with just me, the audio, and the slides. So you want to go from what's the art that we're talking about when we do art to part? Everyone.
The design.
So the art is the design, and what's the design based on? Well, the design. So the design tells us dimensions, but it's not based on dimensions. What's the design based on, Michael?
What the customer needs.
So the design, if in the ideal situation, the design is based on what the customer needs or what the customer desires, right? And we do that because, excuse me, we do that because we want to stay in business. And so we want the customer to buy the things that we're selling, in fact, to continue to buy more of them in the future. So in this class, we're primarily going to look at machining examples of manufacturing. Anybody know why it is that we primarily look at machining examples in this class?
Because that's what we're going to be doing.
So we are going, right, but we chose to look at machining examples. We are going to be doing machining in the labs, but why did we choose machining as our example manufacturing process? So how many manufacturing processes are there?
A lot.
A lot. That's a good answer. So you look like you were putting your hand up, Kirsten. No? Just trying to stay awake by exercising. Okay. So so why is it that we chose machining as our example manufacturing process, specifically CNC machining? Semyon.
Because it's the most accessible to us aside from just assembling parts in a kit.
So absolutely, it's accessible to us here at WPI because we have the machining labs downstairs. So that was a consideration when we're designing the class, that, well, we have access to machining facilities, so we can use machining. But there's a more fundamental reason why we want to use this. Is it? Raphael.
Because it's relatively easy to learn.
Maybe. I think it's relatively easy to learn. I'm not sure everybody in the world thinks that. Why? What's a more fundamental reason, Adrian? Aiden, sorry.
Once you get trained on that equipment, you have a variety of tools to make a bunch of different parts.
So we're going to use this as a way to learn how to use one particular set of equipment. And so we'll learn the process for learning how to use a set of equipment. We'll learn the process for evaluating manufacturing processes in general, and you can apply that across the board. So that's a good reason. So we pick one because we can't teach you everything. Why machining? So once you've figured out the process, it's a relatively fast process. So we talked about, I think, on the first day where you could do your 3D printing. And so in, I don't know, 10 to 35 minutes, you could learn enough about how to use a 3D printer so that you can 3D print something that you've created. But that's something, unless you have a very expensive 3D printer, probably won't be especially functional to you for most manufactured goods. It may take 3 weeks to 3 months to learn enough about the CNC machining so that you can make that first part. But once you can make that first part, you can do it very quickly. So yeah, it is very quick. But why machining in general? What makes machining important to us today? Because we've been doing it for a long time.
Relative to its accessibility, you can make a variety of parts with it.
So you make a variety of parts with it. It's a great way to prototype and make a big variety of parts. Anybody have an iPhone? It's got an aluminum body. The iPhone has an aluminum case. Yeah, it does.
Plastic.
You have a plastic case on the outside of your iPhone. The iPhone itself is aluminum.
No, about 5 foot plastic.
Really? Here's an old iPhone?
Yeah.
All right, so somebody from this century, this decade at least, right? So did you know that those are billet machined? So they're not stamped or cast or anything like that. They're made with CNC machine tools. In fact, there's a Foxconn factory in China where there's 600 identical Haas drill, what do they call it? A drill tap machine. It's a machine tool just like one of the ones we have downstairs. 600 of them in a giant room making iPhones all day long. And they take a block of aluminum and remove, I don't know, what is it, 99% of the material probably to get left over what they keep. If Apple could have figured out a different process to make those parts, they would have figured out a different process to make those parts. Because of the way they designed it, they had to billet machine that part. So machining, I would argue that if you look at any consumer good, anything that you can buy, that you won't find anything that's more than 2 steps in its manufacturing chain away from a machine tool that cut metal. So your plastic iPhone, that plastic was probably injection molded. The injection molding die was cut on a CNC machine tool. So my coffee cup here, paper. Probably didn't machine the paper. The paper flowed over rolls. Anybody ever been to a paper mill? Right? Metal rolls, they were machined. The lid, likewise, the die that made the plastic lid was machined. And so maybe on some objects, you've got to get 3 steps out to find a machine tool that cut metal. But these machining operations are probably the most fundamental operations. Yeah.
How do you machine die?
The die, the metal die.
No, I mean, for the lid, you said that the die for it was machined.
My guess actually on this one is we're 3 steps out. And what we did is we machined the graphite electrode. We used a process called electrode discharge machining. And you take a graphite electrode and you make it the shape of what you want. I'm actually not sure how they make these.
So,
right?
Oh.
But the die is a piece of steel that we mold this into. Right, so all these plastic parts, I don't know if we can get a video or something of some injection molding, but you have a big piece of steel that's got a cavity cut out that's the shape of the thing you want. When you make that big piece of steel, you do machining operations on it. So the thing that we used to make the plastic part was machined.
So it wasn't the plastic part.
Right.
Okay.
Right, although I bet you it was cut with a knife, and the knife was machined. There was a metal removal process that happened there. So we like machining because it's a very fundamental process in our life. In fact, I would argue that the speed at which we can remove metal, so metal removal processes, the speed at which we can do that fundamentally affects our standard of living and the standard of living of everybody in the world. So that's why we use machining as our example process. What are the machining operations that we're going to look at in class? Xavier.
Milling and lathing.
Milling and lathing. We like to call it milling and turning. We use a lathe to do the turning. I do know that if you happen to work at Bausch and Lomb, they across the board call it lathing. I believe because many years ago some engineer made a joke, called it lathing, and everybody repeated it afterwards. I'm not sure why, but that's the only company I've ever been to where they called it lathing instead of turning. So, all right, so we're gonna do some material removal process. So talk to me about turning. What happens in a turning operation? Xavier.
The workpiece is turning, and then you cut out of the.
So if I was the workpiece, I would be turning, right? And there would be some tool acting on me as I'm turning. I can't hold the tool stationary when I turn, right? So the workpiece rotates in turning operations. Let's go. Boy, the internet's slow these days. All right, so we got here some lights off. You guys trying to stay awake? I really don't care what model it is. There we go. So here we have a spinning workpiece. As the workpiece spins, there's relative XZ motion of the tool with that spinning workpiece, and the tool removes material. Is that a turning operation?
No.
Yes.
No. This is a milling operation that's happening inside a lathe. So in this case, we've got so that part is rotating slowly, but the real cutting is happening because of the spinning cutter. So the difference between turning and milling is that in turning operations, the workpiece is rotating. In milling operations, the tool is rotating, and that's what causes the cutting. So the cutting happens when the cutting edge of the tool moves through the workpiece material. It's a Swiss lathe. It's really cool to watch Swiss lathes. We don't have one downstairs. We do have a lathe downstairs that can do milling and turning operations, but it's not quite as fancy as this one. All right, so turning, the workpiece rotates. Milling, the cutting tool rotates, feeds through the workpiece material. Okay. We like to use milling and turning as our example processes because they're very prolific around the world. They're important to our society. What's today's lecture about again? Art to part. And? Art to part and process variables. Right? I think it says art to part and PVs on the lecture. Good. That was my intent. All right. So what are process variables? Michael.
Which tools you're going to use, how you're going to secure them.
So some particular process variables might be which tools we're going to use and how we're going to secure the workpiece in the machine tool. What more broad, what are process variables? Is it shams? Shams.
Yeah.
Shams.
So the factors that affect the features we're trying to make on our machines.
Factors that affect, what kind of factors?
Of the machine or
So factors of the machine that influence how the part comes out. Okay, so those are also process variables. So don't think about machining. What if it's a Big Mac assembly process? What are process variables?
The workers, the hours, the environment of conditions of the workplace.
Right, so you're listing examples of process variables. But process variables are things that we get to control. They're buttons and knobs. They're adjustments that we can control. So is temperature a process variable in a machining operation, right? Because in many manufacturing facilities, we have some control over the temperature of the facility, right? I'm not going to talk about the one downstairs because we have no control there. But there are many manufacturing facilities where we have some control over the temperature. So why would we care about controlling the temperature of our room when we're doing a machining operation? Yes.
Because things heat and cool, they expand and shrink.
So frequently when we're machining metals. Metals tend to have very high coefficients of expansion. And so when they get hotter, they get bigger. When they get cooler, they get smaller. So that's one reason. Yeah, but we don't have to control the room to control that, right? We could control inside the machine tool. So we could build temperature controls into the machine tool to control that. And that's actually one of the reasons that we use cutting fluids or coolants when we're doing a lot of machining operations, is we're spraying that coolant on the workpiece to pull heat out of the workpiece, because believe it or not, shearing off material at that molecular level generates a lot of heat. And so that heat, we've got to get it out of there. Otherwise, we're going to start melting the parts, melting the tools. So yeah, that's one reason. Why else do we care about controlling the temperature of the facility?
Working conditions for the workers.
Yeah, I get cranky when I'm too hot. And when I'm cranky, I don't make good parts. So one reason we want to control the temperature in the facility is to make sure that we make good parts. Yeah.
To avoid damaging the machine itself.
The machine has a computer inside. Anybody that's ever worked with a computer in a hot climate knows that when the air conditioner doesn't work, the computer stops working because it got too hot and it thermal overloaded. So we want to control the temperature to protect the equipment, to make it reasonable for the workers to work there. All right, so temperature is a process variable, a PV. All right, so in machining operations now, what are the we'll take a look at this first, all right? So in our art to part, our motion from art to part. So we've got a representation here of the art, right? And so what is the art made up of? Drawings, what else? Yep. A solid model, maybe. It's not required, but the art frequently includes a solid model, a drawing of the part. What else? So the drawings are there to convey the dimensions to us. So the reason it's not sufficient to simply give the machine shop the solid model is because in the solid model, you can't specify the tolerances. So this right here says that it's 2.25 inches tall, right? Well, 2.26 inches tall works just fine for me too. 2.24 inches tall works just fine for me too. So I can have a band of lengths there. And so the bigger that band of lengths that I give it, the cheaper it is to make. Does that make sense? As a general rule, the larger the tolerance I give on a dimension, the cheaper it is to make that dimension, because the manufacturing person has more options. Right? If it's plus or minus 2/100ths of an inch, if it's plus or minus 0.1 inches, I could use a bandsaw. I could use a hacksaw. I don't really care. Now, I might also have a surface finish tolerance, so I may have to control the surface finish better. But so yeah, so we've got a solid model. We've got drawings. We may also have specifications that are separate from the drawings. So we may have a list of specifications that go with that. And in the purpose, what's the purpose of the art?
You consider a guide of what you need.
To give the machinists, I think we want to do more than just a guide. In fact, when I was a young engineer, probably the first set of drawings that I ever sent from myself to somebody that was going to do the manufacturing, he knew that I didn't know anything. He very easily knew that I didn't know anything. because I gave him a guide. I wasn't specific enough. I think it was a 1/4 tapped hole. I wanted 1/4 tapped holes. And so I specified the drill size as 1/4 tap drill, which is fine, except it depends on the threads that you want, on which tap drill you use to make 1/4. Right, so he knew I didn't know anything. You know what they call us when we're fresh out of college and we don't know anything? Kids with CAD. They definitely call us kids with CAD because we know how to draw shit, right? We're good at CAD. We can put chamfers on everything. Chamfers are cool, right? Especially when you get in that photo rendering in the CAD software. It's all shiny and stuff. Yeah. Chamfers on the outside of parts, or sorry, not chamfers. Fillets. Fillets the one I'm thinking of. Fillets on the outside of parts, expensive to make. Fillets on the inside of parts, cheap to make. Put fillets on the inside of shapes, not on the outside of shapes if you want it to be cheap to make. In fact, sharp edges on the inside of shapes, expensive to make. So these are things that kids with CAD typically don't understand. We try to fix some of that with this class. All right. So this part is this part down here. Get this fired up. Nope, no smoke detectors. We got heat detectors, and if it gets too hot, the sprinklers will go off. I think we're good there. I could have used a lighter, but this was way more fun. All right. So anyway, that part that's in the drawing is this part right here. Who has lab today? When you leave lab today, you will have made one of those parts. Well, I mean, you will have watched the machine tools make one of those parts. Years ago, we first got the CNC machines downstairs. The guy that was director of manufacturing walks into the lab. A bunch of us are standing around, all excited because we're CNC machining. He said, "Hey, what are you guys doing?" "We're machining these parts." "What's the machine doing?" Right, because we were watching the machine, right? We weren't machining anything. The machine was doing all the machining. All right, so so what we have in lab for our first lab is a set of steps by which you will learn to become a CNC operator. Now, I can train a CNC operator in 15 minutes. So it takes about 15 minutes to train a CNC operator. What you have to train them how to do is open the door. Usually there's already a part in there. You have to train them to take the part out, put the new part in, clamp the fixturing. Yeah, actually then open the door, close the door shit, that's optional. The machine will do that for you. So open the door, close the door, put the part in, press the green start button, wait, I don't know, 10 minutes, 3 minutes, 45 seconds, depends on how long the operation takes. And give me a minute, it'll run well. Oh, I got stuck.
What is that anyway?
It's an excuse to have fire in class. This is a thermoacoustic engine. This is the swag that you will make during the labs. I call it swag, and for years I really didn't care if the students made the parts that we asked them to make. I cared if the students learned something about using the machine while they were trying to make the parts, right? I didn't care if the parts came out okay. It turns out, it's been my experience, that the students care if they get to take something home, and that the mothers care if the students bring something home. I mean, usually whoever's paying the tuition bill cares if they get to do that. So, so this is what we call the Y block for our Stirling engine. It's affectionately called the Y block because, well, it's not a V block. A V block is a shape that we specifically talk about in a machine shop where we've got a V shape that's got some block around it to hold the V in place. The whole purpose of the shape is for the V. The block is just to hold the V where we want it. And so what we do with our V blocks is we put something round in them and then we use it to clamp it together. That makes sense? Because if you have two flat edges and you try to clamp a round thing, it's going to move. But if you have three flat edges and you try to clamp a round thing, it'll stay in place better. So this is kind of like a V block, except well, we didn't need the whole block here, so we made it more Y-shaped. There's a few reasons we did that. One of them is because we wanted you guys to get to do some 3-axis machining. And so when we do 3-axis machining, the tool has to move in the X, Y, and Z directions at the same time. When we do, and you will do the programming to make one of these, obviously not for the one that you make today. We're not going to make you do the program and make the part all in a 2-hour lab and have 18 people finish it. But later in the class, this is when we have to worry about the smoke detectors. Later in the class, you'll learn how to actually do the programming for that 3-axis machining. So while you're in lab, either today or tomorrow, depending on when you have lab, you will make one of these, unless something's broken, in which case you'll do it next time. You'll make one of these, or unless something breaks along the way. It has happened before. And when you're not at the machine working on one of those, you'll be at one of the computers learning how to do the basic steps to get started writing a program to run one of the machines. And so when we do this in lab, we have you either at a computer working on something on your own or at a machine tool going through a guided exercise. Well, you do the guided exercises. If Wes is the one doing it and he's with Stephen, Stephen has just finished. Stephen is the instructor. Stephen is telling Wes what to do. Stephen, you can read, right?
I think so.
You good with pictures?
Yeah.
Okay. All of the instructions are formatted such that if you can look at pictures and read basic English words, you can be the instructor. All right. And so we used to do this process called watch, do, teach, where you would actually observe somebody doing it, do it, and then teach it. And we found that the observers didn't observe. They did their phones and they walked around and chatted, tried to get a date for that night or something. I don't know what they were doing. But so we got it down to just watch, teach, or do, teach. So the first person through, one of our peer learning assistants, PLAs, will guide you through that, or will step the first two of you through it. And so if you're the first person, make sure you ask a lot of questions. But you make that Y block today in a production setting where you go through, run the production. So before you do that, you guys have read a little bit about machining operations. You've got, some of you have a little bit of common sense. Some of you may have even run a machine tool before, I don't know. But if this is the part that you have to make, let's talk about the steps that we would go through to make it. So what would you physically do to make this part?
Find a piece of raw material that's bigger than all the dimensions.
Okay, so we need to find a piece of raw material that the part physically fits inside. All right, so we need to define some stock material. That's something we need to do.
It looks like you turn down the end there.
So what you're doing now is you're trying to determine what machining processes you're going to use to make the part, right? So actually, we don't turn it because it's not symmetrical. It's narrower in this orientation than it is in this orientation. And so if you were going to turn something like that, the tool would have to move in and out super fast because we spin at like 2,000 RPMs, 3,000 RPM. So the tool for each revolution would have to do one of these, actually two of those, right? Because two halves of the part. So we typically don't turn something that's not perfectly cylindrical at the end. Not saying it's impossible, but it's certainly expensive. So we won't turn it. But what you were doing is you were deciding what type of processes am I going to do on it. And we certainly make parts that sometimes we turn part of them and we mill part of them. So the first thing we do is we decide that we're going to use a milling machine or a series of milling machines to make this part. All right, so we pick which operation we're going to do. What's the next thing we have to do? We got our stock material. We picked the type of operation.
Write a code.
We're not ready to write code yet. We do have to write code before we get to the machine tool, but we're not ready yet. What do we have to do before we can think about writing the code? Travis.
I'm sure all the machines are working properly.
Then we need to make sure the machines work. I asked the machinist if all the machines work like over Christmas break, and he said yes, so we're good. Did you guys break one since then? Aiden.
Figure out which machine to use.
We will figure out which machine we're going to use. So actually for this process today, we're going to use 2 machines. The reason we're using 2 machines is so that we can have a production flow go through there. We're trying to do a single part flow. The parts are the work pieces, but the parts are also you guys. So our whole watch teach thing, that enables us to do a single part flow through the labs. So we're using 2 machines. We're using a Haas mill drill center, which has a full speed rapid motion of 2,000 inches a minute. That's fast if you hadn't thought of it. 2,000 inches a minute. And we're going to use a Haas VM2 to do. So the mill drill center actually cuts 2 of the operations because it's really fast. At the same time, the VM2 is cutting 1 of the operations. So we have 3 parts in process at any point in time. And every, I think, 4.5, 5 minutes, a part comes out finished. So, all right. So we're going to use 2 different milling machines, but you could do it all in 1 machine. It would just take longer. So we've decided which machine to use. We've got our stock material. What else do we have to do? Before we can make the part. Because we got to hurry up. We're starting labs at 3 o'clock.
Decide on the hold down.
We have to decide how we're going to hold the stock material. Now, looking at this part, can we cut the whole part by putting it in the machine tool 1 time? No. Why not?
Because basically like all the surfaces are going to be.
It's got features that, so those machine tools that we're using are 3-axis machine tools. They can only operate what they can see from the top down, right? So we can, no, can't make it in 1 setup. So we've already determined we've got to have more than 1 setup. What's the first thing that we should do?
I would say cut down top to a roughly cut down the top part of it so you can then clamp down there.
So by the top, you mean the top in this orientation, right? Okay, so we're going to take our stock material. Our stock material is a little bit longer than 2.5, what's the word? Inches. 2.5 inches. It's a little bit longer than 2.5 inches. It's flat on one side and rough bandsaw cut edge on the other side. So what should I do first? Yeah, up in the back.
Face the part.
So we could face the part to make it square all at once. We're not going to bother to do that. The first thing we're going to do, and if I'm lucky, that's the next slide in the presentation. No, but it's close. It's coming up. Coming. I know it is. First thing we're going to do is we're going to put it in the vise. So the stock material is laying down, and one end of it, the bandsaw cut end, is sticking out of the vise. Then with an end mill, we're going to do a contouring operation. Come on. Actually going to do a pocketing operation to remove the V material, and then a contouring operation that makes it the right length and smooths out all the sharp edges. So that's the first operation. In the next operation, we put the side we just made facing up in the vise. Tab. Is it just me or is the internet really slow these days?
The VPN network's always awful.
It's really slow. I clicked, right? Yep, it says waiting. I have more classes than you guys do. Is there anybody that's still having trouble getting access to the materials? There was a few people last night that I still had to fix their reset. When did you sign up?
2 days ago.
2 days ago. Have you tried it since last night?
I tried it last night.
Somebody emailed me last night, and there were like 5 people that had not yet been reset, and I manually reset all those. So send me an email after class today, and I'll check on yours.
Okay.
All right, me1800 labs. Here we go. So it's going to go in the machine. There's a fixture set up where when you open the machine, remember I said we train the machining operator? When they open the door, there's already a part there, so they have to take that part out. So you unclamp the vise, you take your part out. As it's working on it, the first operation makes the V. The next operation does a contour around the edge. It drills and taps the holes, and I believe takes a chamfer end mill and makes a chamfer on the top edge, and it probably flows down the V also, although it's not a straight chamfer down in that V because of the geometries. So it does that. The other thing it does is it machines a pocket right in the center of the part. This picture was taken before we added the pocket to the program. So first operation, make the V. Second operation, make the top, have that contour, drill and tap the holes. That's putting the part in. Loading part. Ah, this is the one I wanted. The button to open the door. Tighten the vise. Just want a picture of the finished part. That's how you put the stock in. So we put the stock material in for that third operation very scientifically by lining up the edges with the blue marks. Don't be surprised if the marks are a different color. We have to draw the marks every time. Then, and so in order to run the program, the machine actually has to know where the part is. And so what's going to happen is the probe will come out, and it will actually, if it's close to the right location, the probe will come out. It will measure its location in X, Y, and Z, and then it will run the program. So the final part, unload the finished part. Looks like this. And so can anybody guess why we have these ridges along the edge of the part here?
Limitation of the tool.
So it is due to the tool, but I could run the operation so that those ridges go away.
Because there's no need to have it smooth every 6 more times.
There was no need to have it smooth. I actually think it looks pretty cool with the ridges. But if it had come out smooth, I would have thought that looked cool too. So how do we make a surface? So this is actually tapered in two directions. It's tapered this way, it's tapered this way as it goes down that surface. What are the physics of making a part that's that shape? What would you do? Yeah.
Use a ball end mill.
We are going to use we're using a bullnose end mill, but you could do it with a ball end mill. And so a ball end mill, you guys looked at end mills, right? Eraser. And end mill goes out like that. There's some cutting flutes that go up it, right? As it spins, and if you looked at the bottom, you'd see some cutting flutes there. So as it spins, those cutting edges move through the workpiece material, pull the chips away, removes material. Right? So if I'm using this, and I want to make a shape that looks like that, that's hard to do, right? So how can I make this shape? Remember I said that the fillets are hard to machine on the outside of parts, expensive to machine? How could I make that shape? I could take a grinder to my end mill. I could make my end mill that shape. It's a little bit more sophisticated than that.
You can use the sides of the bit.
So the other thing I could do is I could take an end mill that's got some kind of a radius down there. Now, there's a lot of reasons I like end mills that have a radius right there. Those sharp edges at the corner of an end mill, they break off really easily. There's very high stress concentrations at those points. So if it's rounded, it wears out more slowly and more predictably. So I could take an end mill that's got a radius down here, and I could cut 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 here, I could cut here, I could cut here, cut here, here. And what I end up with is a surface that looks like this. Is a surface that would be blue if I had a blue marker that looks like this. Which is what we see here, right? Ridges like that because we're taking an end mill. I think the radius is 5/8 of an inch of the bullnose end mill that we're using. So you could have an end mill that's like this. You could have one that's spherical on the bottom. So it's got a hemisphere on the bottom. Do the same thing with it. And do that. So how do I then make it smooth if that's my process? And that is absolutely the process we use here.
Use smaller and smaller.
Yeah, you just step down smaller and smaller amounts. If you step down a small enough amount, the human eye can't see the roughness that you left behind. What happens when I do that? Takes a long time to finish. Exactly. So if you're making a lot of parts that have a fillet on the outside, and sometimes you want the fillet on the outside because the marketing guy says that's what the customer demands, not just because the kid with CAD drew it that way. Sometimes you need the fillet on the outside for mechanical reasons. If you're making a lot of those parts, then what you're going to do is you're going to get custom-made tooling that has that radius, so there's just one zip around. But you got to have a special tool for each radius. If you're making a few parts, or if the customer doesn't care if it's a fillet or a chamfer on the outside edge. So this tool, I don't know, that tool costs $100. That tool costs $15. So if I can make it with the $15 tool, I will. All right, so we're gonna no class tomorrow. No lecture tomorrow, let me be clear. There is lab tomorrow, no lecture tomorrow. We're going to continue this topic on Tuesday next week. That's when we meet again, right? Go ahead.
Question, the assignments Friday, where are they posted?
They will be on my WPI, what day is today, Wednesday? Today. They go live Wednesday evenings, the Friday assignments.
Tomorrow, lecture.
It was never scheduled, so it's not canceled.
So there are on the WPI calendar, there are 21 slots for classes.
So we scheduled in over excess capacity, so we didn't always have to have class. Hi. Yeah, let me turn this off. Yeah. If I remember how.
Wes.
Just gonna leave it there.